We want to evaluate the geometric series or state that our series diverges. Our series is k equals 0 to infinity of 1/3 to the k. So in this case, r is 1/3 and a is 1. We're not multiplying this geometric series by anything out here. It's just 1. And because the absolute value of r is less than 1, that means that our series converges, and it converges to a divided by 1 minus r. So we know that a is 1 and r is 1/3, so 1 over 1 minus 1/3, that's 1 divided by 2/3, so that is 3/2. Here we have the series k equals 4 to infinity of 3 to the negative 2k. So first let's convince ourselves this is a geometric series. So 3 to the negative 2k can be written as 1 over 3 to the 2k, which can then be written as 1 over 3 squared to the k, and 3 squared is 9, so that's 1 over 9 to the k, which can be rewritten as 1/9 to the k. So this series can be rewritten as k equals 4 to infinity of 1/9 to the k, which definitely looks geometric. So to determine if this geometric series converges, there are a couple ways we can go about doing this. First, we should notice that this series starts with k equals 4, not 0. So what this means is that our series, when we write out some terms, looks like 1/9 to the 4th plus 1/9 to the 5th plus 1/9 to the 6th, and so on. If we factor out a 1/9 to the 4th from each term, we can rewrite this as 1/9 to the 4th times 1 plus 1/9 plus 1/9 squared, and so on. So now this series is the series k equals 0 to infinity of 1/9 to the k. And this is a geometric series with r equals 1/9, and the absolute value of r is less than 1, so it converges to a over 1 minus r, which in this case a is 1 and r is 1/9, so it converges to 1 over 1 minus 1/9. So that means that this series equals 1/9 to the 4th times 1 over 1 minus 1/9, which we can rewrite as 1/9 to the 4th times 9/8, which can be rewritten as 1 over 8 times 9 cubed, which is 1 over 5,832. Now there's another way that we can go about finding the sum of this series. If we start with our series, k equals 4 to infinity of 1/9 to the k, we can shift the index using a substitution. So to do that, we want I equals 0 to represent k equals 4. So we're going to let k equal I plus 4. So that means that the series is now written as the series from I equals 0 to infinity of 1/9 to the I plus 4. And using the rules of exponents, we can rewrite this as the series from I equals 0 to infinity of 1/9 to the 4th times 1/9 to the I. So now we have that A equals 1/9 to the 4th and R equals 1/9. So this converges to A, which is 1/9 to the 4th over 1 minus R, and R is 1/9. And this also equals 1 over 5,832, as it should. So that's another way that we can go about finding the sum of our series. And we have one more option. Again, starting with our series k equals 4 to infinity of 1/9 to the k. We could write this as the series k equals 0 to infinity of 1/9 to the k. And then subtract off the first 4 terms. So we're subtracting off 1 over 1 plus 1/9 plus 1/9 squared plus 1/9 cubed. So now we have this geometric series, and the sum is 1 over 1 minus 1/9. And then we're going to subtract off 1 plus 1/9 plus 1/9 squared plus 1/9 cubed. And that will also get us to 1 over 5,832. So these are 3 different ways that we can think about how to find the sum of a series where the sum doesn't start at 0. We want to write this decimal as a geometric series and express its value as a fraction. So we have 0.07 repeating, which is 0.07, 07, 07, and so on. So this looks like 0.07 plus 0.0007 plus 0.000007, and so on, which we can rewrite as 0.07 plus 0.07 times 1/100th plus 0.07 times 1 over 100 squared, and so on. So we can write this as the series from k equals 0 to infinity of 0.07 times 1 over 100 to the k. Here we have the series k equals 0 to infinity of 3 times 2 to the negative k. So first let's convince ourselves that this is the geometric series. So we can write 2 to the negative k as 1 over 2 to the k, which can be written as 1/2 to the k. So that means that this series is really the series from k equals 0 to infinity of 3 times 1/2 k. So we see that this is a geometric series where a equals 3 and r equals 1/2. So since r is 1/2, the absolute value of r is less than 1, so our series converges, and it converges to a over 1 minus r. So a is 3 and r is 1/2, so 3 over 1 minus 1/2, and that is 3 divided by 1/2, which is 6. So our series converges to 6. We want to evaluate the series from k equals 1 to infinity of the quantity k divided by k plus 1 minus k plus 1 over k plus 2. So let's look at what this series will look like by writing out the first few terms. It's going to be 1 divided by 2 minus 2 divided by 3 plus 2 divided by 3 minus 3 divided by 4 plus 3 divided by 4 minus 4 divided by 5, and so on. So you might see that some of these terms are canceling out and think that this equals 1/2. But this series does not equal 1/2. We need to be careful, and we need to look more closely at our partial sums. So let's look at the first partial sum. The first partial sum is 1/2 minus 2/3. The second partial sum is 1/2 minus 2/3 plus 2/3 minus 3/4. So our nth partial sum is 1/2 minus 2/3 plus 2/3 minus 3/4, and so on, plus n minus 1 over n minus n over n plus 1 plus n over n plus 1 minus n plus 1 over n plus 2. So we see some of our terms will cancel, and we'll be left with our first term and our last term. So S sub n equals 1/2 minus n plus 1 over n plus 2. Now we're going to look at the limit as n goes to infinity of S sub n. So the limit as n goes to infinity of 1/2 minus n plus 1 over n plus 2. And this limit, so this equals 1/2 minus 1, which is negative 1/2. So that means that our series from k equals 1 to infinity of k over k plus 1 minus k plus 1 over k plus 2 equals negative 1/2 and converges. We can also note that k divided by k plus 1 minus k plus 1 over k plus 2, if we found a common denominator, we could rewrite this as k squared minus 2k minus the quantity k squared plus 2k plus 1, all divided by k plus 1 times k plus 2, and that equals negative 1 divided by k plus 1 times k plus 2. So we could rewrite this series as the series from k equals 1 to infinity of negative 1 over k plus 1 times k plus 2, which equals negative 1/6 minus 1/12 minus 1/20, and so on. So this note will be helpful later on when we'll start with a form that looks like this and is one fraction, and use partial fraction decomposition to rewrite it as a telescoping series. Here we have the series k equals 3 to infinity of 4 divided by 4k minus 3 times 4k plus 1. Looking at this series, we see that there is a product in the denominator. So it looks like this could be rewritten using partial fractions into two separate fractions. So looking at that, we have 4 divided by 4k minus 3 times 4k plus 1 equals a over 4k minus 3 plus b over 4k plus 1. So then we have a times 4k plus 1 plus b times 4k minus 3 has to equal 4. A times 4k plus a plus b times 4k minus 3b equals 4. Now we split this out into a system of equations, things without k and things with k. So 4a times k plus 4b times k has to equal 0 because there's no k term over on the right side. And a minus 3b has to equal 4. So we have 4a plus 4b equals 0, and a minus 3b equals 4. So a plus b equals 0. So that means that a equals negative b. And if we plug that into our other equation, then negative b minus 3b equals 4. So negative 4b equals 4, and b equals negative 1. Since b equals negative 1, that means that a equals positive 1. So we can rewrite this as using partial fractions as the series from k equals 3 to infinity of 1 over 4k minus 3 plus negative 1 over 4k plus 1. So now we have a telescoping series. If we look at the nth partial sum, we get 1 over 9 minus 1 over 13 plus 1 over 13 minus 1 over 17 plus 1 over 17 minus 1 over 21, and so on, plus 1 over 4 times n minus 1 minus 3 minus 1 over 4 times n minus 1 plus 1 plus 1 over 4n minus 3 minus 1 over 4n plus 1. So terms are going to cancel out, and we're going to be left with s sub n equals 1/9 minus 1 over 4n plus 1. So now we want to find the limit as n goes to infinity of s sub n. So the limit as n goes to infinity of 1/9 minus 1 over 4n plus 1, and that equals 1/9. So our series converges to 1/9. Here we want to determine if the series from k equals 0 to infinity of inverse tangent of k minus inverse tangent of k plus 2 converges or diverges. So looking at the nth partial sum, that would be inverse tangent of 0 minus inverse tangent of 2 plus inverse tangent of 1 minus inverse tangent of 3 plus inverse tangent of 2 minus inverse tangent of 4, and so on, plus the n minus 1 term would be inverse tangent of n minus 1 minus inverse tangent of n plus 1 plus inverse tangent of n minus inverse tangent of n plus 2. So a lot of these terms are going to cancel out, and we'll find that we are left with S sub n equals the inverse tangent of 0 plus the inverse tangent of 1 minus the inverse tangent of n plus 1 minus the inverse tangent of n plus 2. So then we look at the limit as n goes to infinity of S sub n. So we're looking for the limit as n goes to infinity of the inverse tangent of 0. So we're looking for the limit as n goes to infinity. Inverse tangent of 0 is 0. Inverse tangent of 1 is pi over 4 minus inverse tangent of n plus 1 minus inverse tangent of n plus 2. Now the limit as n goes to infinity of inverse tangent of n plus 1 and n plus inverse tangent of n plus 2, those are both pi over 2. So we get the limit as n goes to infinity of S sub n is 0 plus pi over 4 minus pi over 2 minus pi over 2, which is negative 3 pi over 4. So that means that the series from k equals 0 to infinity of inverse tangent of k minus inverse tangent of k plus 2 converges to negative 3 pi over 4.